This is the summary created from the video. Lecture 54, Sustainable Cloud Computing I. The lecture begins by explaining the time intervals for peak-off-peak and island modes in DC microgrid simulation, along with the battery and capacitor status during each mode. It outlines the challenges of identifying peak periods and highlights the need for a control strategy to manage devices and avoid grid stress. The simulation results are then discussed, showcasing bus voltages, currents from PV, battery, and ultracapacitors, as well as grid voltages and currents. Various time instants are presented with zoomed views, and the isolated mode operation demonstrates the microgrid's voltages and currents without the grid. The hardware implementation and experimental results are presented, with DC microgrids operating at 100V and 48V, exhibiting autonomous operation and characteristics. The practical implementation scales down grid voltages from 380V to 100V, and the impact of numerous microgrids on the national grid is explored under peak and off-peak conditions. The integration of DC microgrids with the national grid and the IIT Roorkee distribution system is discussed, involving energy management analysis, simulating large networks using smaller representative models, and enhancing voltage profiles and line utilization through optimal placement of DC microgrids. Power hardware-in-loop experiments are conducted for real-time microgrid studies. A case study on coordinated voltage control with a DC microgrid integrated into the IEEE grid is presented. The setup includes PV, battery, loads, converters, sensors, and amplifiers with a closed-loop power hardware-in-loop PHIL experimentation setup. Power characteristics are compared with and without voltage control methods. The concluding remarks summarize the key points from the lecture on hardware implementation. Case studies simulated in previous lectures. Simulations executed on hardware for energy management. Integration with the IITR Roorkee distribution system and larger networks. And the implementation of coordinated voltage control schemes using DC microgrids. The key takeaways highlight the case study showcasing coordinated voltage control with a DC microgrid, the integration of DC microgrids with the national grid for energy management, the modeling of practical campus distribution for DC microgrid integration, the exploration of the impact of numerous microgrids on the national grid load, the conduction of power hardware-in-loop experiments for real-time studies, and the implementation of autonomous smart grid operation in isolated mode. Please stay tuned for more summary videos.